So, welcome to this 40th webinar about analysis and optimization of Vlasiator at production scale. And in the next 30 minutes, what I want to share with you is basically what kind of insight we got from an analysis we did of Vlasiator at production scale and what kind of things we can learn from this. So to start, let me start a bit with what we're going to talk about. So first of all, I will introduce quickly what is Vlasiator, why, how did this analysis happen? And then I will go a bit into the tools and methodology we used to actually get insight. Then we will discuss quite in detail two aspects of the analysis that I picked because the actual analysis is a bit bigger, but I boiled it down a bit to focus it a bit for the webinar. And then we will talk about a small optimization that we did that actually improved the performance quite a lot of a particular region of the code. And I will show you a few pictures of that. So how did we end up doing this very large scale, and I think one of the biggest POP analysis, or at least in the POP 3 cycle, done so far? So this is basically a collaboration between the Plasma Pepsi COE and the POP COE, where the Plasma Pepsi COE focuses on all things plasma, and one of the applications is Vlasiator. What they simulate is basically the plasma near the Earth. So what I brought for you is basically a picture. I hope you can see my cursor. This blue dot in the middle here is the Earth. And then what we see here in very nice colors is not plasma, but it's actually the computational load as computed by the internal load balancing mechanism. And we can already see that we have some very high variances. So this goes up to e to the 4 from 100. And we can basically see different things happening. We can see the magnetosphere being deformed a bit. We can see plasma in the upper atmosphere layers and so on. You can already see from this picture that the computational domain is quite big. And additionally, so to the three-dimensional space, so 3D space, they also have a three-dimensional velocity space on top. So this is actually a full 6D resolved Vlasov simulation, which is quite expensive in terms of memory. Let's talk a bit about Vlasiator. Vlasiator simulates near-Earth plasma. It's written in C++. They do have a CUDA port, but the version I used uses only MPI and OpenMP for parallelism, so typical hybrid code. They have annotations available and timing measurements available through FileProf, which is a library they use. For this restart file, so this basically is a simulation they did on Mati of a production run, and the idea was to analyze what we can see with the BSC tools or as a POP COE, what we can see where they could improve performance. So we basically collaborated. They shared with us the 5 terabyte restart file from this production run, where the simulation is not in initial state, but we have a fully developed sparse adaptive mesh in both spatial and velocity space. In total, this input takes about 55 terabytes of memory. So the smallest number of nodes we can run on is actually 250 nodes here in Mare Nostrum 5 in a general purpose partition in Barcelona. If you want to know a bit more about the machine, you can, in the PDF version, this is a link you can click that will take you to a paper introducing the machine. We did very similar setup to the production run they used. So we used 14 MPI processes with 8 OpenMP threads each, bound to the 2 sockets, so 7 per socket. And basically the threads were pinned to the cores close to in the same NUMA domain. SMT is disabled. In the production, they run with SMT enabled. We disabled it because we didn't see any benefit on our machine. They used an AMD machine, we used an Intel machine. There might be some differences there. Then for the methodology, normally what people do, or what is a typical approach, especially with the BC tools in this case, is to just trace everything and then basically look at the trace and try to find the focus of analysis by looking at repetitive structures or regions of interest in general, and using this as using the initial trace as a thing that guides you towards what you want to analyze. In this case, at 500 nodes or 56,000 processors or CPUs, this is not really easy to do. Just for the purpose of an academic exercise, I actually traced that, and I got roughly 1 terabyte of intermediate trace. So the thing that then needs to be merged to become a real trace. So I expect trace sizes between 500 and 900 gigabytes for the 250 and 500 node runs respectively, which is of course way too big to be reasonably analyzed. So in this case, we choose a bit of a different path. We already knew that we want to analyze a time step. So what we did is basically put FIPROF regions. So the FIPROF regions that we had of the different code regions, we just put them in TALP. Now, if you don't know what TALP is, don't worry. I will explain it to you. TALP is basically a profiler, but instead of just giving you timings, it also reads puppy counters for cycle sense instructions, and it gives you parallel efficiency metrics based on the programming models you use. So you get like the typical pop metrics, but without having to get a trace. There's also other tools that do this. I just use TALP. Then based on this instrumented version of the code, we basically did scaling runs, and we end up with an efficiency table, which you will see in a second, per region. And then based on these initial efficiency that we gathered with TALP, we will just do the selective tracing of only the region we actually want to analyze in depth. And this leads to a very analyzable number of gigabytes, which was 14 gigabytes for the biggest trace we've gotten. For the tools that we used, as this is a BSC analysis, we of course rely on the BSC tools, Xray, Paraver, and TALP. But I want to mention that this is basically very, very similarly doable. So the methodology applies very similarly. You can just get a profile with Cube, have a look at it, a profile with Scopy, have a look at it in Cube, then get a trace with Scalaska of only those regions. So this is very similarly applicable to also the other POP tools, I think. The hardware counters were gathered using Papi. Just want to mention that, not really important for this analysis, just if people are curious. And in terms of overheads, runtimes in these larger scale simulations vary a bit, but we had an overhead around 5 to 10%, depending a bit on the tool and on the run and how stable the baseline performance was. So we do have measurable overhead, but within reasonable bounds. Before I show you the lots of traces that I got, and we will analyze them in depth, we first need to understand a bit what is a Paraver trace, because we will have a look at them in a second. So on the y-axis, you can see the objects, which I just labeled them MPI process 1, MPI process 2, MPI process 3. And on the x-axis, you can see time. What I did not label because of lack of space is basically that every MPI process has 8 threads. And we can see this in the end, where we can see that some threads finish a bit late. For example, here the 4th thread seems to finish a bit later than the others. Okay, here the 2nd one. What we see here is useful duration. So what is useful duration? In PEP, in POP, we basically have the notion of the CPU is doing something useful or it's not doing something useful. Something not useful normally is when it's doing an MPI call or being in the OpenMP runtime. So what is useful duration? Useful duration just means how long does my CPU, does my resource run without calling into any runtime library. And we can see that in this case, all 8 threads run for roughly 1.5 seconds or 1.2 seconds in MPI process 1, and a little bit less in MPI process 2, and a little bit less in MPI process 3, without calling any MPI function, and all in the same OpenMP parallel. This can be very easily verified by just looking at another parallel visualization that it provides, which is basically what is the OpenMP parallel function that is being executed. And we can see all of those processes and all their threads execute actually this calculated acceleration function. Then the second parallel region that we have is calculate moments, which we can already see is a bit more fine granular. So we have probably around 500 milliseconds average duration here compared to the 1.2 seconds that the calculate acceleration took. And last but not least, we see that there's white space here, okay? White space in these plots that I'm going to show you means that the CPU is idle or not doing something useful. Idle, not really, because normally it's in an MPI wait call and an MPI barrier. And therefore, we can visualize also the MPI calls the CPU is doing. And we can see that, for example, here, the MPI process 3 becomes white. This is because it's in an MPI wait all call, waiting for its communication to arrive. So for you as a takeaway, whenever we see white in useful duration, that means that we're in a runtime call. So all of those threads are basically doing nothing because they're either waiting for MPI to come back to them or because they're in an OpenMP scheduling thing. For this particular trace, we are only using MPI. So all the white space is basically due to MPI. So with this out of the way, let's focus on the analysis and what kind of insights we can get from tracing at production scale. First of all, I want to show you a bit the structure of a typical time step. So how does it look like? Which are the most interesting or most time-consuming functions? And then we will have a look at the scaling results to decide which subregions we want to focus the analysis on. And then we will have a look in depth into the spatial space translations and into the field solvers as the 2 regions that we chose. So first of all, this is what a typical time step looks like for Vlasiator at 500 nodes in Mare Nostrum 5. So the time step region is called propagate to propagate the simulation state along. And we can see that the biggest region here in green is the spatial space region, which takes around 50 to 55% of the time. Then the second region that is very time consuming is the propagate fields, which are the field solvers where we solve the electric and magnetic fields. And then the velocity space updates, which take around 15%. And the rest of the 4% of runtime per time step are basically updating the system boundaries in different regimes of the simulation. Now, if we take this input and strongly scale it, we will end up with a table very similar to this. Bear with me, there's a lot of numbers. Don't despair. I will explain them in a second. So first of all, we have to note that propagate is a time step, right? And then we have the 3 children. So because of space reasons, I just put the time step region here, but this basically includes all of the other 3 regions. So propagate is the farther or the higher up region of spatial space, propagate fields and velocity space. This also makes sense if you look at the timings. So this one is, for example, 17 seconds at 500 nodes. And then spatial space takes around 9 seconds. Now, I want to highlight a few numbers that we're going to discuss. And the rest is, if you're interested, we can discuss them in the Q&A later, but I will not go into detail now. So first of all, we will only look at the 500 node column, which is the 56,000 CPUs that we have here. And we can already see that, first of all, parallel efficiency in propagate is not that good. What does parallel efficiency mean? Well, parallel efficiency basically, and this is a strong simplification, but basically means that we only use 21% in this case of the machine, or 70% in the case of the spatial space. And what do I mean by machine? I mean CPUs. So only 17% of the time the CPUs are doing useful computation and not spending time in MPI or OpenMP library calls. If we look at the two different factors that basically compose this parallel efficiency, we can see that load balance is with 39% the worst one compared to communication efficiency with 43. Looking at the propagate fields, we can also see that it's even a bit worse. So here we only use 16% of the resources or of the CPUs we have in this region. And load balance is one of the main contributing factors why we cannot use the resources efficiently. If we now just look at the runtimes and at the speedups, we see that actually we have a superlinear speedup. Okay, this is very typical because we basically scale from a base case which is not 1. So we hide all of this inefficiency that we have in the base case already and just scale relative to that. And we can see that we scale super linearly. So we have a 2.1x speedup, even though we're only using roughly 20% of the machine in the time step. Interestingly, in the spatial space, we see that most of or all of the superlinear scaling comes from the spatial space. And in the spatial space, mostly the computation scalability is responsible for the speedup. So we just run at a higher IPC, means our CPU is able to retire more instructions per cycle. This is mostly due to cache effects. So because we strong scale, the working data set gets a little bit smaller, roughly half, and then we fit more into L3. And since this is a bandwidth bound code, we get a little bit more effective bandwidth, which increases the IPC a bit. We can also see that load balance improved a bit, which is curious, but just a curious side note. Similar effects for the propagate fields. There we have 5% increase just because of IPC and a little bit of frequency apparently as well. Okay. With this out of the way, we basically say, or we basically chose to analyze the spatial space translations as they have very bad parallel efficiency, and the propagate fields, which also has very bad parallel efficiency. If we look at the velocity space with 43%, it's not great, but it seems the best out of the 3. So we only chose those 2 for analysis. Now, again, we see the whole time step, and now we basically see the useful duration of this region. And without understanding too much what we see, we can already see that we basically have a lot of white here. And then we have 3 very repetitive structures with some light blue, some light green following them. So what we say, and this is actually a very valid approach, is to only focus on one of them, knowing that we do spatial space translation, and this is actually the Z direction, the Y direction, and the X direction that's being updated. So with this, we will just go to the next slide and just focus on the Z direction now. So whenever we talk about spatial space, we assume that it generalizes, but it looks like it generalizes very nicely. So now, what do we see in this picture, and what is the basic analysis that, or what is the insight that we can get from these kind of graphics? So first of all, we can see that the spatial space translation, what happens? First of all, semantically on a computation base or numerically, they basically gather data from the neighbors. They do some stencil-like computation, and then they spatter it back to the neighbors, the new values. Okay, this is conceptually what's happening in the spatial space translation solver. Now, what do we see? First of all, we can see this initial phase which seems to use a lot of MPI weight alls here. So if we look at the MPI timescale, we can see that we have a lot of MPI weight alls, and this is basically the communication. Vlasiator communicates a lot of data. This was also a surprise for the developers. They didn't know that they communicated that much data. But so this is only the set directional update on 500 nodes, and we communicate roughly 6.3 terabytes of data. Per process, that's on average roughly 900 megabytes. And per node with the 14 processes that we have on a node, that's like 12 and a half, 13 gigabytes per node. On Mare Nostrum, we can move roughly 12 and a half gigabytes per second. So we expect this move of data to take roughly 1 second, a little bit less probably. And indeed, we roughly run for 800 milliseconds in this phase. So overlapping computation and communication here is very beneficial, especially because we move so much data. They were already aware of this, not to that extent though. Then the second thing we can easily see in this picture is that we have very different shades of green and blue. What does this mean? Well, this does mean that different amount or different processes spend different times in the computation phase, because remember, this is the very long free-running computation phase. So what we basically see through this color shading is that we have load imbalance, and I can give you some numbers. So the most loaded process, which is probably one of those that arrives very late here to the barrier, he computes for 1.6 seconds, okay? The average process computes for roughly 400 milliseconds. So we can already see that if the maximum process takes around 4x of the average, that's probably not a situation you want to be in. The Vlasiator people were very aware of this. It's just the nature of 6D sparse simulations that you cannot really predict how big, for example, the velocity space content is. So this is a very hard problem to solve. And then in the end, we see that we do have the update remote neighbors, which is a two-phase or two-step communication. They do. So yes, but basically what we told them, or what we provided insight with, is that this is heavily load imbalanced, and to the extent that it's very visible here at the synchronization point that we're waiting for only a few processes. By the way, this changes for every direction and for every time step. So you cannot fix this very easily with static load balancing. And we communicate a lot of data. So the overlap would be very, very beneficial for this part of the code. Then, now moving on to the next region of interest that we said we want to analyze, basically the field solver, so propagate fields. Where again we can already see some structure, but let's have a closer look. So in here, we basically see in the beginning some weird behavior, in the end some very white regions and blue spikes. And again, white means idle CPUs, blue means very long computation without an MPI or OpenMP call. And the initial thing is actually feeding things they computed in the spatial space translation, converting them, integrating them, and feeding them into the field solvers. This is done using a third-party library, which doesn't support OpenMP threading. So this is actually serial code. The developers were already aware, and I think they already fixed it, but this is an artifact that we look at in this version of the code that we're having. Very similarly, in the back, initial setup, copying the solved fields out again, depends heavily on this library that is not OpenMP supported. So we have serial code and heavy load imbalance. So what we did is we basically took this very iterative looking region and we identified it as iterative part of the actual solver. And we chose to look at that. And here we can basically see a rescaled version of it. And because it looks so regular, we just chose the fourth iteration to look at it, assuming that probably all will be same. Then what do we see? First of all, we see that we see some kind of combs. Okay, so some weird thing where apparently there's some waves or something like this happening. And we see a similar thing if we just look at the one iteration. But then we can also see that here seems to be a collective. So because all the threads wait and start again, or the processes wait and start again here at the end of one iteration. So we will just have a look at what causes the very late people or the late processes to come late to the barrier. So what we do is, instead of assume by time, we now assume by processes. So instead of looking from MPI process 1 to 7,000, we only look from MPI process 6,500 to 6,620. And we want to do this a bit more in detail. So let's switch slides. And we can already see that we should have, and I'm looking now at the top picture, we should have this nice lockstep pattern where we execute the same color or the same shade of green nicely below each other, right? And this actually becomes more obvious if we look at the OpenMP parallel function, and we can see, for example, that the calculate Hall term should be a straight line in theory, and as well as the calculate upwinded electric field in theory, or in the best case scenario, would be a straight line. What we actually see is that we have these regions here, these code regions, that seem to delay the whole computation phase by quite a lot. So what we did is we can basically zoom into it a bit more and now just look at one of those offending very long OpenMP regions. And this is now just 3 MPI processes. So we can see the MPI process 6602, 6603, and 6604 with the 8 threads each. And we can see that 6602 basically has a lot more work than all the other MPI processes. So it's basically MPI load balance that we're seeing. But unfortunately, somehow, it also is very bad OpenMP load balance, because all the work is being allocated here in the last thread and here in the second to last thread by accident, or by sheer unluck, I would say. So not only is there's MPI load balance because this process has apparently a lot more work than these two processes, but it's also very badly distributed across the OpenMP threads in that process. Yes, so MPI load imbalance, and unluckily, only one OpenMP thread got all the work, which then delayed the whole communication chain, and then we arrive very late to the barrier. So as a short recap on the analysis part, basically in spatial space, the developers should really focus, or let's put it like that, it would be very effective to try to overlap communication and computation, especially when we use very large simulation runs like this. And a thing that will also pay off is trying to load balance the computation part, because we saw that we have very long waiting times and very inefficient use of resources because of the MPI barrier they have. Then in the propagate field, so in the field solvers, we saw some serial code at the start and the end of the field solvers, which I think in theory should already be fixed. And then the propagate magnetic field basically has MPI load imbalance and a very unfavorable OpenMP work sharing clause. So this is the feedback that we basically provided to the developers. And this concludes the analysis part of my presentation. I will now move forward to what we actually did achieve in terms of optimization. So after reporting this to developers, they were like, we know probably what's happening. Let me implement a solution. And this is basically what we will try to understand now and see how it affects the simulation. So in an advisory study, what we do in POP is we show the customer, in this case, the Vlasiator developers, a problem. They implement the solution, and we assess if the solution worked nicely for the given problem. And what we did is basically was the magnetic field boundary handling that was computed like this. So basically, it's a very thick for loop that goes over the three-dimensional cells that they have in a parallel fashion, and then checks if the cell is a boundary cell. And only if it's a boundary cell and they want to compute that certain direction right now, then we issue the compute. We can already see, so they collapse the two loops here, but we can already see with this early return in the conditional that this might lead to some threads not getting work if they're really unlucky. So what they actually did, and the source code is available if you want to check it out. What we actually do now, and please don't copy this code, it will be horribly wrong. This is pseudocode that looks like C++. So what we do now is we basically just accumulate all the indices that we want to solve in this vector, and then compute, iterating through this vector. So what we do here is, the work instantiation is actually the actual work distributed across all the threads, instead of having the early returns, because we already captured them here. It's a lot of code for, I think, quite a simple concept. So now, remember, this was the way the field solver, or one field solver iteration, looked, with these very long single-threaded executions where we had very bad OpenMP work sharing. Now, after applying the fix that we just saw, it looked like this. So first of all, we can see that these regions here nicely folded back into the lockstep pattern that they are supposed to be. And if you have really good eyes and you're a bit a pro in looking at Laravel traces, we can already also identify the parallel regions that we created. So this long computation that was running here, that was basically delaying all of the other threads and processes, now it's this parallel region where all the threads are working on the problem. And we can see that the MPA load balance actually is not that bad if you use all the threads to solve it. So the threads, so the OpenMP threads kind of help mitigate the MPI load balance that we initially had. And now we can see that we are not the one arriving the latest to the barrier, because here is already the second iteration coming in of the field solver. So this is only one iteration, but we can also have a look at more iterations. So this is now the full 12 iterations of the field solver that it took in this example. And we can see that here, basically, we have the same processes always being the latest to the barrier here and delaying it. And after the fix, we can see quite nicely that we run in a very nice lockstep pattern. And what we see is actually a 28% speed up of those 12 iterations. This then translates into a roughly 10% speed up of the whole region, because there's this initial thing and the end thing, which we didn't fix, but yes. This also shows in the efficiency metrics. So if we just take the efficiency metrics of these 12 iterations, what we mostly see is, first of all, our parallel efficiency goes up from 34% from 34 to 43. And then most importantly, the MPA load balances improves a lot to 85%, which is very good. Now communication efficiency is low, which would warrant another assessment, but we stopped here for now. And we see the speed up of 28% as well in the average runtime. Now as a summary, so with our tools, we were basically able to provide a quite detailed analysis of how Vlasiator is using the machine and how it's performing in terms of resource usage at 56,000 CPUs in Mare Nostrum. For the spatial space, it could really benefit from overlapping computations communications because it's so communication heavy. And And the spatial space stencils experience heavy load imbalance, which is what they already were aware of. And this is a very hard problem to solve. We are also trying to solve this problem right now using DLB in a prototype, in a proof of concept, which is another second level service we do in POP, where the results are not yet as robust as I want them to be. So there's no data on that yet, but I expect to have something there soon. And then in the propagate fields, basically what we could easily achieve is that through this advisory study that we did, this is also a second level service, we improved the field solver performance by 10%. And we could even explain why it was faster. And yes. So with this, I only have the typical acknowledgement slides left, and I think we can stop the recording and go for the Q&A.
Yeah, thank you, Valentin. Actually, we record the questions as well. I don't see any questions so far yet in the chat. So if you just want to ask your question directly, please unmute your phone and start directly. And now someone is coming on. The first question came in. So there is a question on, is there any attempt to port the code to GPUs?
Yes, as far as I know, this effort was also supported by Plasma Pepsi, and I think they already run productive GPU simulations now in Lumi. But the version we used, or this was done at the beginning of Plasma Pepsi, so 1.5 years ago, this analysis, and continued throughout the project lifetime. But yes, the code is available on GPUs as well.
Okay, any other question? You can also ask questions just on the POP services if you don't have questions directly on the presentation. Yeah, so looks like everyone is happy. So this was an example basically how POP can provide various services to application developers, and also is another example of a successful collaboration between COEs on the European level. If there's no more questions, I don't want to steal any more time to everyone. So thanks everyone for joining, and potentially see you back to our next POP webinar, which is planned around early May. Okay, bye-bye.